Hello, everyone. Okay. In this week's lessons, we're going to be moving towards how to use derivatives to create graphs. So to introduce the idea of where they're going to be useful, a problem you might have had in the advanced functions course was to sketch a polynomial function like this. Okay. So, looking at the equation, I know my y-intercept is positive 12. I'd want to factor this, right? So when I factor it, those are going to be my factors. Okay, and now I can start producing a rough sketch, right? So I'm going to have roots at positive 1, and at positive 4, and at negative 3. Okay, and I noted my y-intercept would be up here somewhere. It's positive 12. Okay, but after that, that's kind of all you have. Okay, we know, right, the function has to turn around, so it might look something like this. Okay, but I don't know exactly where that is, right? Okay, so you may have done some, just some testing, plugging in some numbers to get some of the points, to get a rough idea. Okay, but you're not exactly sure where those points are. Okay, when we had the quadratic, right, going back to grade 10 and grade 11, right, it was always easy because the vertex was always halfway between the roots. Okay, but that is not necessarily the case here. Okay. However, and maybe you can see this coming already, we started to talk about the idea of, where little maximums and minimums occur, and that's where the tangent line is briefly going to be 0. Okay, it kind of flattens out at that point. So that's the idea, is we can use derivatives, right? Find where the slope of the tangent is 0, and that will pinpoint exactly where that local maximum or minimum will be. Okay. So today's note is on what's called the first and second derivative tests. So these are a series of tests that gives you, more information about the function other than just where its roots and where's its y-intercept. So first, a little definition here. Okay, a critical number is a number c such that f prime of c is equal to 0. Okay, so the point c and f of c, so the original point on the function, is called a critical point. Okay, so like we had in that picture, right, if there's a cubic function of some kind, then this point here and this point here are going to be critical points of the function because that's where their tangent line would have a slope of 0. Okay, so example 1, here's another cubic function. We're going to find the critical points of that function. So I just have to take my derivative, so f prime of x. Okay, and at the moment we're polynomials, so this is fairly straightforward. Right? It's going to be 3x squared minus 8x plus 2. Okay, now I need to set this equal to 0. Okay, and see what I get for my critical points. Okay, so this is quadratic. Okay, I can attempt to factor it. Right, multiplies to 6, adds to negative 8. Okay, I don't think that's going to work. So in this case, I would actually have to go to quadratic formula to figure out what those points are. Right, so x equals, I would have 8 plus or minus the square root of negative 8 squared minus 4 times 3 times 2 all over 2 times 3. Okay, so I've got 8 plus or minus, so let's see, we'd have 64, subtract 24 over 6. Okay, so under the root sign, I'm going to have 40, which would reduce down to 8 plus or minus 2 root 10 over 6. So I'm going to have 4 plus or minus root 3 over root 3 root 10 over 3. Sorry, not 3 root 10, just root 10. Okay, not nice, but those are my two critical points. So those are locations where the slope of the tangent is 0. Okay, so that tells me that if I were to draw my cubic function, that one of these points could be a max, one could be a min. Now I say could be because there's actually three kind of situations. Okay, so this next picture here, this is not a cubic function. Okay, this is at least fifth degree because there's one root here, and three roots here because it smooths out for a second. Okay, but this is showing the three kinds of things that can happen, right? The slope of the tangent over here would be 0, and I have what's called a local maximum. Okay, there's a peak in this region of the function, but it's not the highest point on the graph, right? Because the graph keeps going off this way. So it's not the absolute max, but it is a local max. It's the highest point in an area. Okay, on the other side, okay, this is a local minimum. Okay, it's the lowest point, kind of in its neighborhood there. Okay, but in the middle here, where I have that triple root, okay, it does smooth out, right? The tangent line would be 0 in the middle here, but it's not a max or a min. Okay, so having a critical point doesn't guarantee it's a maximum or a minimum, but it could be. Okay, so this is where the first derivative test comes in. Okay. First, we're going to talk about the test for increasing and decreasing functions. Okay, consider the interval AB of some function. Okay, so I have a block. So when we say interval, what I mean is, again, if there's my function, okay, I'm talking about some block, maybe from here to here. What's going on here? Okay, if the derivative is positive for all x in that interval, then the function is increasing on the interval. Okay, and if the derivative is less than 0, so negative on that interval, then the function is decreasing on that interval. Okay, so again, to explain what's going on there, okay, maybe I'll do a rough sketch of that thing I just had up there that goes like this. Okay, so going from left to right, up until that first maximum, my function is increasing. Okay, it's saying if that's true, then the derivative is greater than 0. Okay, well, why is that? Well, if I try to draw a tangent line anywhere in this section, it is going to have a positive slope. Okay, it doesn't matter where I put it, it's going to have a positive slope. It might not be very steep, but it is going to have a positive slope. Okay, in the next stretch of my graph to here, okay, I am pretty much decreasing the entire time, just about. Okay, it briefly flattens in the middle. Okay, but in that stretch, wherever I try to draw a tangent line, okay, it's going to have a negative slope. So that means my derivative has to be negative in this region. Okay, so that's what this is saying, right? If I know in my derivative where it's positive and where it's negative, that tells me when my original function is increasing or decreasing. So for the first derivative test, if we know a critical number, okay, if our derivative switches from positive to negative at that critical number, then that means we have a local maximum. Okay, right? Because if the function was positive first, right, or sorry, the derivative was positive, that means I was increasing. Okay, if it switches to negative, that means it's now decreasing. So the point in the middle had to be max. Okay, if it switches from negative to positive, right, so that means I was decreasing first and then increasing, then that means I must have a local minimum at that point. Okay, so that's what that's saying. So let's take this function and put that to work. We're going to find and classify the critical numbers of x cubed minus 12x. So first, before I can do that, I need to take my derivative. So f prime of x is equal to 3x squared minus 12. Okay, I'm going to set this equal to 0. Okay, which means I'm going to factor it and solve it. So I've got 3 times x squared minus 4. So 0 equals 3x minus 2, x plus 2. Okay, therefore, x is equal to plus or minus 2. Okay, so those are my critical numbers. Okay, the critical numbers are plus or minus 2. Classify, I want to figure out if they are a max or a min. Okay, So to do this, we need to figure out where this function, or sorry, where my derivative is positive or negative. And a nice way to do that is to do an interval chart, okay? Which again, you would have learned about in advanced functions and maybe before that. So in my function, I have a stray 3, I have an x minus 2, and I have an x plus 2. Okay, for my intervals, I look at my roots. So my first root is -2. So my first interval is from -infinity to -2. Okay, my second interval is between -2 and +2. Okay, and my third interval is from 2 to infinity. Now I look at the sign of each of these pieces. Okay, for the 3, it's a +3, so I always get a positive value there. Again, for these brackets, right, I'm testing a value. So for example, I just pick some number within this range, which is almost anything. Okay, if I try -3, for example, if I plug that in, I have -5. So this is negative. Okay, for x plus 2, if I plug in a -3, I get -1. So this is also negative. Okay, and proceeding through, I'm going to get this when I fill that all in. So in summary, for my derivative, okay, I have a positive, and then I have a negative, and then I have a positive. So what does that mean? Okay, well, for at -2, what happens? It switches from positive to negative. So it means my function was increasing, and now it's decreasing. So that means there is a local maximum at -2. Okay, for the other one, okay, it was decreasing, now it's increasing. So that means that 2 is a local minimum. Okay. Again, as a rough sketch, if you think about what a cubic function can usually do, what this is suggesting is my function must look something like this, right? I have a max here and a minimum here. Okay, the next thing we're going to talk about is what's called concavity. Okay, concavity describes the direction that the curve is kind of opening. So if you go back to, parabolas, okay, we would call this is concave up. And this is concave down. Okay, on a cubic function, like the one we just drew, okay, when I have something like this, right, it is concave down in this section, and it is concave up over here, and somewhere in between it switches. Okay. You can also do this with rational functions, right? If I have like a basic reciprocal function, it would be something like this. Okay, this section is concave down, and this section is concave up. Okay. So we can also test this part. So let f of x be a twice differentiable function. The second derivative exists on the interval a to b. So I had to be able to take my second derivative here. Okay, if the second derivative is greater than 0, so positive on that interval, then f is concave up on that interval. Okay, if the second derivative is less than 0, so negative on that interval, then the function is concave down, okay, at the interval. Okay, and finally, if we have an inflection point, which I'll explain in a second, then f double prime of x is equal to 0. Okay, an inflection point is basically where it switches. So like this little point right here that I dabbed on the cubic function. Okay, it was going concave down, and now it switched to concave up. Okay, physically, if you're drawing this curve, okay, you can kind of feel your hand, I don't know, twist. Like you can feel you're drawing in a different direction when you go around this point. Your hand is being pulled a different way when you're drawing the curve. It's kind of hard to describe. Okay. Now again, to explain why that's happening, let's talk about this. Okay, if f double prime is positive, okay, so if it's positive, that means that the rate of change of my tangent line slope, right, the rate of change is positive, which means it's increasing. Okay, if I were to draw tangent lines on this parabola, okay, originally I have a steep negative slope. It becomes less negative, starts to be positive, more positive, very positive. So my tangent lines have an increasing slope. They went from a large negative, right, to being less negative, and eventually it's positive. So that's why it's concave up, because my tangent line slopes are increasing. Okay, for concave down, it's the opposite. Right? These start as steep positive slopes. They get less positive, flatten out, they become more negative. So the slope of my tangent lines are decreasing. Okay, so that means my second derivative is negative or less than 0. Okay, so now we're going to describe the concavity of the function we were just talking about. And we did a rough sketch, so we know what we're looking for here. Okay. But to review, right, our first derivative was 3x squared. Our second derivative okay, so I take this and differentiate again, and I get 6x. So, same idea. First, I'm going to look for an inflection point. So that means my second derivative is going to be equal to 0. Okay, and that's a very quick divide by 6, and x is equal to 0. So there's an inflection point there. Okay, now I'm going to do up another one of those little charts. Okay, so my only root is 0, so my two intervals are negative infinity to 0 and 0 to infinity. Okay, and I have a 6 and I have an x. So the 6 is always positive. Okay, the x is negative in that first interval and positive in the second. Okay, so my derivative is going to be negative here, positive here. Okay, which means on my original function, okay, this is going to be concave up. Okay, I can't really, sorry, this is concave down, and I can't really fit the words in here, so I'm just going to draw it, right? That's concave down in that interval, and this is concave up in this interval. Okay, so that means when I'm drawing that function, okay, there's an inflection point here. Okay, and the stretch before it has to be concave down, so it looks something like this. And the stretch after that has to be concave up and look something like that. Okay. Okay, because of the whole thing with concavity, we could also use the second derivative to test for a local min and a local max. Okay, right? Flipping back here, I know that in a concave down region like this, okay, well, if I have a max or a min there, it's going to have to be a max. Right? If it's concave down and there's a part where the tangent is 0, then it has to be a max because it's facing this way. Similarly, if it's concave up, well, if there's a critical point there, it's going to be a minimum because it bottoms out somewhere because of the shape. So that's what the second derivative test says. Okay. If f prime of c is equal to 0, right? So your first derivative is 0, and your second derivative at the same value is positive, then you have a local minimum. Okay, and that sounds opposite to positive, but that's what happens. Okay, right? Again, what that's saying is my first derivative is 0, so the slope of the tangent is 0 at that point. Okay, double prime being greater than 0 means that it is concave up. It looks like this, so therefore this has to be a minimum. Okay, similarly here, if f of c is equal to 0 and double prime is equal to, sorry, is less than 0, then it has to be a maximum, right? Maybe something like this, but it's concave down, so it's a max. Okay. If they're both 0, so it's a critical point and it's an inflection point, then this test doesn't work. And we don't know for sure what's going on. Okay, so you use something else to check, like say the first derivative test. Okay, what's probably happening if they're both 0 is that you have one of these from that graph we showed a while ago. Okay, right? This is both has a tangent of 0, and it's concave up over here and concave down over here. Okay, so it's probably that, but we don't know for sure. Could be something really weird. Okay. Okay, so example 4, we're going to verify what we found in example 2 using the second derivative test. Okay, so again, let's just list out our derivatives here. We found that our critical points were at +2 and -2 when we work with the first derivative. So to test if it's a max or a min, okay, I go to my second derivative and I start plugging in the values and see what happens. Okay, so I do f double prime. We'll start with 2. Okay, that's 6 times 2, which is 12. Okay, this is a positive result. Okay, that means in that interval, okay, it is concave up. Okay, so that means that 2 is a minimum. Okay, right? Because it's a positive result, it has to be minimum. Okay, similarly, for f double prime of -2, okay, I'm going to get -12. Okay, it's negative, so x equals -2 is a local maximum. Okay. All right, so there's a lot to digest there. Okay, but this, right now, just using the tests to identify what's going on. So here's a few questions. It's from a few different pages of just using those tests to gather information. Okay, in the next couple lessons, we'll then turn that into graphing and how you can use this to make a really nice graph. Okay, thanks for watching. And if you have any questions, please let me know.